For homework 3, part B, we're going to be simulating our non-steady state distillation column in Python. We've imported NumPy, solve IVP, and make subplots for using later. And we have some of our initial conditions and things we've determined before we started for our situation. We want 7 total number of stages, so condenser, 2 above the feed stage, 2 below, then our reboiler. We have our Francis-Weir constant, which we'll use for our Francis-Weir equation calculations, and then our initial Molar holdup in each tray, which we've set to be 1.2. One thing to note for this is that our reboiler and condenser are going to be 10 times this amount, so we'll account for that later. We have our relative volatility, which we are assuming to be constant, and we'll use this to calculate our Y composition from our X, our molar flow rate going into our feed stage, which is 1 mole per second, our initial mole fractions, 0.5, our feed composition, our distillate flow rate, and our reflux ratio. Another thing we need to calculate is our bottoms, which is just equal to our feed minus our distillate. And then we can move on to our liquid at the top. So this is going to be stages 1 and 2 primarily. And this is equal to our reflux ratio times our distillate. We know that the molar holdup in this area using our Francis-Weir equation. So knowing what's flowing over, we can determine what our initial molar holdup of our top sections are going to be. So this is going to be equal to our LT divided by our Francis-Weir constant, WC. This is going to be to the power 2/3 because this is rearranging our Francis-Weir to get our holdup instead of what's leaving. So we'll add what's held up using our Francis-Weir, and to that we will add our M0 to give us our molar holdup in our top in terms of liquid, and then we will do our liquid in our bottom sections. So this is going to be the feed stage and below. So what's going to be in our bottom will be our liquid from our top, and then from this we're going to add our Q times our feed because we have our feed, and then we also have our feed composition, so all the liquid of that feed is going to be part of our L bottom. Then the next thing we do is we'll get our molar holdup of liquid in the bottom, MB, which will just be LB Francis-Weir constant 2/3 power plus our initial molar holdup. We know that our VT is going to be equal to our LT, so our liquid coming out of the top plus what's going out. So all of the vapor that goes up is either returned as top liquid or turned into distillate. And then we know that our V bottoms is going to be equal to our VT minus 1 minus Q, parentheses, 1 minus Q times our feed. And this is because all of our vapor going up in our top section is equal to all the things from the bottom plus our feed composition, that is vapor, so 1 minus Q. So everything in the bottom is only equal to our what's at the top subtracted from our initial feeds. So so the next thing we can do is set our initial conditions. So our initial concentrations are going to be equal to NP full. We want N number, so 7, and then our initial composition of Z, and then we want our initial molar holdups, which is going to be equal to an array. So our first one is going to be our condenser. Our holdup is going to be our M0, multiplied by 10, because we want our condenser and reboiler to have 10 times the amount. We will then have 2 MTs, so top stages. We'll have another one. We will then have our bottom stages, so MB, our feed stage, which is going to be MB because our feed is already accounted for in that stage, another MB, and a third one. And then lastly, we'll have M0 multiplied by 10 one more time to give us our reboiler molar holdup. What we need to do now is define a function that will calculate our changing molar holdups and our changing compositions. So we'll define our right hand side as a function of time and our vector, which will be our initial holdups and concentration, or holdups and compositions. And what we'll do is we'll split these into our holdups and compositions, which we'll do by NP split our vector, then we'll split this into two pieces. So the next thing we're going to need to do is create initial arrays for our dm, dx, dmx, our liquid phase, and our vapor phase. So our dm is going to be equal to np zeros like m. Our dmx equal np dot zeros like x. We'll have our liquid equal to our np zeros like m, and then our vapors will be zeros like m once again. Now we should have everything we need for our initial arrays of each of these. Moving on, we need a way to calculate our y composition from our x's, which we can use our relative volatility to do. So our x composition times alpha, our relative volatility, will be divided by our 1 minus x times alpha, our relative volatility, one more time, which will give us our y compositions from our x's. Now for our liquid phase stages, or what our liquid flow rate for each stage will be, our liquid coming from our zero stage or our condenser is going to be equal to R times D. Our liquid coming from stages, our second stage all the way up until our second to last, is going to be calculated using our Francis-Weir equation. So our FWC multiplied by our m's, or our m's, and we want just our first one, or our second one through our second to last, and then minus our m0. So our initial. So this will calculate our liquid change for our second all the way up into our second to last. But this needs to be to the 3/2 power, or 1.5. So we get that. And then lastly, we need to have our liquid from our reboiler, our bottom stage. So our L minus 1 is going to be based off this flow rate again. So, or it won't be based on a flow rate, however, it will be based on a controller, which we will set our value of Kc, which for now, I think 1.5. Kc is equal to 1.5. So our L is equal to our bottoms plus our Kc multiplied by, and we want to take our difference, so our current molar holdup of our reboiler, which would be m -1 minus our mi -1. So our current molar holdup of our reboiler minus our initial holdup of our reboiler. So using this, it will use a proportional controller to change what our B will be. One thing we need to do is make an if statement to make sure our flow rate is never negative. So we'll call this our BC for B controller. So if BC is greater than or equal to 0, we want our L minus 1 to be equal to BC. However, else if our L minus 1 is, or our BC is less than 0, we want our L minus 1 to be equal to 0 instead. Okay, I think that looks good so far. So now we have all of our liquid being accounted for. Our very first stage, our condenser, all the ones in between, and our last stage, the reboiler. Next, we need to do what we just did with our liquids. So determining what's going to be flowing, but doing this with our vapors. So we know that our vapor coming out of our condenser is going to be equal to 0. So we can determine that. And we'll do np dot row concatenation, and we'll start with our first stage. So our condenser will be 0. We know our VTs in this case are going to be the same as up here. So we have our LT plus D, which we know our LT plus D is just R times D. So we have our VTs, and then we know our VBs will be the same as up here, which will just be our VT minus 1 minus Q plus F. So now that we have these, we can add these into our concatenation for our initial, or not our initial V values, but our flow rates of vapor. So we will have 3 VTs, so our top stages, our top 2 stages, and our feed stage will all be VT because the vapor feed is counted in our feed stage. So we will have VT, VT, another VT, and then our bottoms, so our VB, VB, and VB for our bottom 2 and our reboiler. We can now calculate our DMs. So our first, or our second, all the way until our second to last are going to be equal to, so what's going into them? So it's going to be our V n plus 1s. So our V's, and then this will be our third all the way until the end. And then to this we'll add our liquids from the end all the way, or the beginning all the way up until our second to last. And then from this we will subtract what's going out. So in this case it's going to be our V's from our current stage all the way up until the second to last, or second, and then again subtracting our liquids from second to last stage. So we have what's coming in the vapor, what's coming in the liquid, and then what's leaving in vapor and leaving in liquid. For our feed tray, it will be the same as what it currently is. However, we will need to add our feed, so we don't need to do anything extra to this because this is in moles and this is also in moles. So just third plus that. We know our condenser 0 is going to be equal to our condenser will be equal to what's coming in. So this will be our V1, and then what's leaving is our distillate, and there's something else. Distillate and L0? Our distillate and our L0, which is just R times D. So D and then R times, okay, yeah. And then for our reboiler, so our DM -1, this is equal to what's going in and out. So what's going in is going to be our liquid from our second to last stage. What's leaving is going to be our liquid from that stage, and then what else is leaving is going to be our vapor from that stage. That should be our equations for our changing molar holdup. Our DMXs will be very similar, however, this time we'll need to be sure to include our mole fractions this time. So we have our V, take this, paste it. So our V2, so what we need here is times our Y, 2 to the end. We need here times our X, -2, or the beginning to the second last. Right here we need our Y's again. Y from 1 till our second to last. And then here we need our X's, 1 until second to last. So we move on to our DMX, our feed tray. So this is going to be equal to plus equals our feed times our initial mole composition fractions. So I think that's all we need to do there. And then our DMX of our condenser 0 is equal to our V1 times our vapor fraction 1, Y1 equals, and then from this we are subtracting our D and L minus 0. So minus, and put this here, we have our D plus L0. D plus L0, so what we have here, minus, and then this is multiplied by X, and then dmax of our -1, a reboiler, is just equal to what we have to start for dm, L multiplied by our Y2 multiplied by Y1, -1, -2. And then, oh, these are both x's. X, X, and then our V multiplied by our Y, -1. See, so now we have our equation here. To get our dx's, we need to first take what's over here. We need to subtract our dm dt multiplied by x, and then we need to divide by m, giving us dx. So we need to take our, this is our dmx minus our x times dm dt divided by m. So we can now do that. So our dx is equal to dmx minus our x's times our dm. And this is all divided by our m's. So we have x and m. And now what we want to return is our, we started with m first when we had picked, so our dm and our dx. Now we can use our solve IVP and our initial values to hopefully find a solution for this. So our result is going to be our solve IVP of our function, so right hand side. I guess we need a time to do this over, so our Tn would be 500, and okay. So our right hand side, we want this to be from 0 to our T end. We need our initial guesses, so this is going to be our MP row concatenation of, we have our m first and our x second, so this will be mi xi. We'll use our method equal to radu, and our dense output will be equal to true. So I guess we can see if this works. Where's our problem at? Uh-oh. Setting an array element with the sequence. Oh, does this just need to be x 0? 2 and 14, 2 and 14. We need to split something. This needs to become one thing, so we can unpack it later. Pm return np.r this. That works. Okay. So our t-plot will be np linspace from our 0 to our t end. We want 50 points. Our m's and our x's will be equal to our res.solution of our t-plot. However, this needs to be split, so np split our res.sol t-plot. We need to split this into 2, and our axis will be 0. Line space, linspace, linspace. So now we can check our m's and x's. So, okay. 12s, so these look alright. What we can do now is plot these. So our figure, make subplots. We need 1 rows equal 1, columns equal 2, 1 row, 2 columns, and then for I in enumerate, then we want to zip our m's and our x's. So now we can count with I and have our m's and x's separated. We want to fig.add underscore scatter. Our x values is equal to t-plot. Our y's are going to be equal to for m comma x and m's and x's, our y is going to be equal to m, and And then our name is going to be f string, which will be our m, and then a space, and our I, or no space. And again, do the same thing, but add our x's, so our x, x, and then we also need the position, so row 1, column 1, and then here will be row 1, column 2. I is not defined. I enumerate mxi, failed syntax, for I. Oh, you might want a comma. Come on. How could I? And then, hopefully, see what we want to see. So, we have here is our holdups and our compositions. Why is this one going to -3? I think this is getting multiplied by something it shouldn't be. Okay, so after an unbelievable amount of time looking for what could possibly be causing our compositions to reach -3 and 5, it has come to my attention that this equation should be a plus and not a minus, which you would not believe how much of a difference that would make. But now what you can see here is our holdups in each tray, so we can take a look at our M0, which should be our condenser. As you can see, this is constant at 12, which is what we'd expect because we are reaching a steady state. And then we can see our M1, which looks to be fluctuating. However, this is a very, very small amount, and it's become pretty steady at a state just above our holdup. And then we can see our concentrations again. You can see our x's will spread out just a bit based on which tray they are in. So we have more liquid near the top at our condenser, and then as we get down, it's more and more vapor as it's being reboiled and becoming vapor.